that horizontally, and we put it vertically, and we put a dot whenever the same word is in that particular position, you'll see to be or not to be. And there's going to be a vertical, diagonal line. Well, to be is repeated. So we have another diagonal over there, another diagonal over there. Okay, now let's say instead of to be or not to be, we took, say, 32 bytes from a file. And instead of this 32 bytes in a file is the same as this 32 bytes file in a file, or this 32 bytes is different than this one, we actually make it kind of fuzzy. We can use something called the Levenshtein string distance to tell us how similar or how different, on a scale from 0.0 to 1.0, how different or similar are these two values. What kind of patterns do we get now? We get some weird stuff showing up. Like, file formats really just, these are languages, these are tongues. And, hex is meaningless. But this stuff isn't. Now, understanding these patterns is really hard. In the paper, they describe various things that might show up. Like if you have a stream of messages A, B, C, D, E, F, G, I, and then all of a sudden it goes backwards, I, H, G, F, E, D, C, B, A, you're going to get like this big X thing that shows up. Or you might get these squares that show up. Or you might get breaks that show up. But I mean, no one knows. No one has ever expected this type of complexity because, this stuff was never built for anything that had this many patterns, It was either being used for text, which is surprisingly unpatterned, or it was being used on the genome, which is patterned, but in ways that defy human comprehension. So, how can we actually make these pretty pictures useful? Little piece of advice, 98% of visualizations are totally useless. The cool part is trying to get to that 2% that it actually can be used for something. So let's figure out what kind of questions we can ask that might determine, is there a reason we should do this? Well, the two things we can try to do are A, identify formats blindly, and B, guide a fuzzer. Let's start with the first. Question 1, do different files actually appear different? And does the appearance reflect the existence of internal structure? If we just saw like noise no matter what, this wouldn't be helpful. Well, here's a Java class file. Here's a .NET assembly. CNN's homepage. Packets. Note, we can actually see packet starting, packet starting, packet starting. We can actually see where one packet stops and another begins. Imagine how hard it would be to analyze a packet dump if you didn't actually know where they start and stop. Well, in files, you have that all the time. An individual file format contains all these little tiny chunks, and you don't know where one starts and another begins. Packet dump's a great example of it. With no knowledge of libpcap, I can still tell you when they begin and end. Kernel 32, chromosomes. Like I told you, this was a genetics hack. The Legend of Zelda. So yeah, I think we win that front. But now, do different instances of the same file format appear similar? Text. If you actually take books from Project Gutenberg, text actually isn't very patterned. Now, you'd think it would be, because English is fairly low entropy, it's 1.3 bits per character, but you don't usually open a book and the same paragraph is in chapter 1 as in chapter 3. You don't usually see the same paragraph repeated over and over and over again. And so you actually don't get much self-similarity. The symbol clusters don't really align. But law is not text. Holy crap, code is code. No, seriously, code does not look anything like any book you would ever see. Legal code is very much, we want to say the same things in same ways so we are very clear we mean the exact same message. Legalese is something else entirely, and it straight up shows up in the data. Warning, do not fuzz the law. Or your genome for that matter. HTML. Now this is really interesting. If you look at HTML, it actually has a lot of internal redundancy. First of all, tags. Tags are constantly being repeated over and over again, and thus you get these very small-scale repeats. You also get larger clusters because most websites now are built with templating engines. And so they're constantly looping over, repeating the same expression of a message. And this shows up, and you see this on pretty much no matter what website you go to. You can be like, oh yeah, that kind of looks like HTML. So that's kind of cool. Java class files. Now these aren't as consistent. Now binary code tends to be the most complex thing that you'll analyze. Excuse me. That still has a visible, very deep structure to it. The interesting thing is, you are very dependent not just on the compiler. At the end of the day, a file format is a shell for content. And content varies pretty heavily, especially inside of code. This was actually a class factory, and this class factory looked like nothing else I'd ever seen. I have no idea why it looks so different. But clearly, you can have quite a bit of variability that comes not at the format layer, not at the compiler layer, but actually what the heck is the code trying to do. x86 is actually pretty consistent in sections. It tends not to be handwritten. There are exceptions in this room. So as such, complex instructions are emitted in a pretty regularized form. There is an exception. Someone said, you should totally grab like some really tight hand-coded assembly. And I'm, of course, demo scene. Awesome. So I grab a 64K demo, and I grab it, and you know how you don't see anything there? Well, that's because it's just a big mass of gray. You know what compression does? Takes all those nice patterns that you were looking at and just sort of gets rid of them. So you've got this little tiny block of like x86 at the beginning, and yeah, the rest of it's just like unpacker stuff. So you can pretty quickly see packed code. Nintendo games. Gotta love the Nintendo games. So these things actually look really familiar. Like if you actually compare them visually to one another, they have this very blocky pattern. But Mario looks totally different. I don't know what the hell they're doing. Again, output's highly dependent on the compiler and highly dependent on the actual content. I actually think they're doing some kind of packing here, personally. So, do different instances of the same file format appear similar? Well, they can. Similar content certainly looks like itself. But remember, you're measuring the content. You're not necessarily measuring the file format. So, final question. Does one format embedded in another make itself apparent? Well, this is actually kernel 32. And these are 3 different sections of the same file. What's going on here? Well, let's actually take a look at a large file. And I have no idea if this is going to work. And I'm absolutely sure I don't have time to do it, but that's never stopped me before. Maybe. So the great thing about hacking graphically is you end up with like these images that are 1,000 pixels wide and 138,000 pixels tall. Yes. All right, so check this out. This is shell32.dll. This file's 8 megs and is an ungodly mess. Awesome. So check this out. We're just gonna browse through it real quick. Oh wait. Interesting section. Oh, this is all x86 stuff. This is actually a new rendering mode that I created because I needed something that was vertical. Oh, interesting section. Oh, what the hell just happened here? What in God's name are they embedding in here? Wait, what was that? Was that a big vertical line? Repeats. So the way this mode actually works, this is actually cool. We're still going through our file. As we go down, each pixel, that's 32 bytes in. So if it's 100,000 pixels down, that's 3.2 million bytes in. So you have this thing right here, but as you go horizontally, you're looking backwards in bytes. So you have to, if you go 32 bytes, if you go 500 pixels to the right, that means you went 500 times 32 bytes back in the file. And so you can see there's repeats at that offset off. And we can just go through this entire thing and start seeing all the various internal structure that this one particular file is containing. Now, I'm not saying this is perfect, but it is a... If I showed you a hex dump, would you even see differences? I don't think so. So, complain all you want. Hex sucks. So, multiple distinct sections are clearly visible in a way that hex cannot show. Awesome. Now, fuzzer guidance. This is where we actually start breaking stuff. Can we actually locate byte offsets where one section ends and another begins? Well, why would we want to do that? Fuzzers break parsers. There are two kinds of parsers in the world. There are those that were fuzzed during development and those that die really quickly. So, fuzzers break parsers. But there are many subformats to a format, and there are many subparsers to, an actual file format parser. There's all these little paths that you'd want to go after. To a rough level of approximation, when you fuzz a subformat, you fuzz that parser and that parser alone. You want to fuzz one chunk of the file at a time. So if we can split the file up into clearly different, chunks that are clearly different languages, we can go ahead and we can fuzz all these internal chunks separately. We turn it from a problem where you have to, multiply out all the potential changes that you'd have to make into one where you add them out. I fuzz this section, this section, this section. So it's like code coverage. So can we actually locate these byte offsets? Well, very simple math. I alluded to it earlier. You take your file, and you just go, let's grab a pixel. This is on the absolute version, not the tilt shift. Well, let's see. We're going to go, this is interesting, this block here. It's at 507 by 507. Well, 507 times 32. The interesting section starts 16,000 bytes in. Oh, look, this square is 570 pixels across. All right, 570 times 32. The interesting section is 18,240 bytes long. Let's get some external verification here. Let's see what the heck this data actually is. We're going to go ahead and we're going to look just a little bit before 16.224. We're going to look at 16.100. And what we actually see is a bunch of stuff that's like 0381, 0382, 0383, whatever that is. And then all of a sudden, right here on hex 60, totally new format. Totally new parser is going to be reading that. This is actually API calls in kernel 32. So you could potentially find this via hex dump in this particular example, but I argue it was a heck of a lot easier to go, whoa, something happened there. So the goal is use Hardcore, which is the name of the tool that I have, as a first knife for locating interesting regions of a file to fuzz. We have a compressed data file here, a video file. And it's 4 instances of related formats. And it's actually really cool. What section should you go after to fuzz? Now, video formats, they're compressed, but they tend to have headers. Well, how do you find these headers? Well, it's very nice to just look at the file and go, done, hit, fuzz that, fuzz that, fuzz that, fuzz that, and just like pick it, grab the offset and go, rather than look through the hex dump, look for something that has an odd number of nulls, look at, just visually take it as hex. I think this is a lot faster. We've got millions of years of evolution giving us a third of our brain for visual processing. Can't we possibly break something with that? So, can we visualize and compare fuzzer operations via dot plots? Well, a major use of dot plots in bioinformatics is actually to compare one genome against another. Thus far, what I've shown you is autocorrelation. That's where you take a file and you compare it against itself. We can actually do something much more interesting, and that would be cross-correlation. That's when you compare a file to a different file. Now, most of the time, this yields crap. However, suppose you're looking at 2 versions of the same file. One from before a patch, one from after. It turns out, most of the time, most things stay the same. Just little tiny things happen to differ. We can see it. Before, we had that line of equality. And actually, it's going to be kind of hard to see, but hopefully you'll be able to see it a little. Before, we had this line of equality, to be or not to be. No matter what those words were, we would always have The first byte's always equal, the first word's always equal to the first word. The second word is always equal to the second word, and so on. Well, now that's not the case, because now we have two different versions, two different texts, two different content. And sometimes they're the same, sometimes they're saying to be or not to be, but other times words